Hi, this is Narhari again. Today we'll talk about basics of launch vehicles. Launch vehicles, I mean the ones you've heard from Indian Space Research Organizations or the Ariane or everything else. Basically rockets which are used to put useful payloads, sometimes warheads also into the orbit. So basically, in the broadest sense, the launch vehicles lift payload from launch pad, place them into first part is low Earth orbit. From there, they can be pushed into any other orbit. We'll talk about that a little later. And if it's a missile, it's not going to put it in orbit. It's going to take it to a height. And then from there, you use the gravitational force into a ballistic mode and you'll go and reach the target. So, for example, recently the North Korean missiles, I think Hwasong 7 was launched, and they claimed it reached a certain height in some 670 kilometers altitude, and then distance of 7,000 whatever those numbers. So, in a missile, the idea is not to put anything in orbit. The idea is to be able to reach the target. Whereas in a civilian application, like what ISR is developing, the idea is to put payload into orbits. Now, payload could be Earth sensing payload. It could be remote sensing payload, which looks at the natural, stuff like forests and water availability and stuff. Or it could be communication satellites like GSAT, GSAT-1, and all that. Or it could be even carrying a telescope like the Hubble and everything else. So, a payload is something which is going to be useful package in that orbit. So that the launch vehicle's main job is to put that into that orbit. So the first step is to put it in what is called a transfer orbit, that is at an elliptical orbit from where it is taken into different places. Here the main performance requirements basically are the thrust of the rocket, weight of the rocket, so the ratio thrust to weight, which is important, which we'll talk about a little later, total impulse, and also the total velocity increments. So these are the main things which are called the performance metrics for any launch vehicle. So the basic task of propelling space vehicles and certain weapon systems, as I mentioned earlier, is best accomplished by rocket engines. One thing, they carry their own oxidizer, and they're independent of ambient atmosphere. So they provide a high energy system. A rocket engine can be viewed as basically two parts: one, a combustion chamber, and a nozzle. The combustion chamber is responsible for producing hot gases at high pressure, and these high pressure gases are then expanded to into larger kinetic energy by expelling the gases at high velocities. The velocities could be close to 2 to 3 kilometers per second. So remember, in the school we were told how a rocket works by taking a balloon, blowing air into the balloon, and suddenly releasing it, and the air in the balloon would expand to the neck of the balloon, and then propelling the balloon randomly here and there. The same thing is affected here. The while the air in the balloon is a finite quantity, and after some time the balloon collapses. Here you continuously produce hot gases by burning what are called propellants. That could be fuel oxidizer combination, and that's the job of the combustion chamber. A nozzle is exactly similar to the neck of a balloon. In this case, of course, I'm simplifying it. The nozzles and the combustion chamber are extremely complex mechanical devices, but the basic idea is to produce a lot of hot gases which can then be expanded through the nozzle at very high velocities. So some examples of launch vehicles. The left one, the one you see here on the left, is of course a missile which can be launched, and this is another missile which can be launched. These are Indian missiles, and of course this is an launch civilian launch vehicle. So you can see it's much larger, and the payload is somewhere at the top here, and you also have multiple boosters. So different kinds of launch vehicles. The very first launch vehicle, Saturn V, which was used for Apollo 11 thing, that's a different kind of thing. But all of it boils down to some kind of a combustion chamber and some nozzles. So the earliest use of rockets in warfare, as documented, was by Tipu Sultan sometime in his period when he fought against the British. But their rockets were very, very crude, simply metal tubes filled with gunpowder, and then, of course, swords attached to it, so that when the rocket would go rather randomly into the enemy territory. Of course, in those days, the war was more like infantry soldiers, so the rockets would cause havoc. Nobody likes to see a sword swinging in front of his face randomly at high speeds. Now, but these were later. One of the unburnt rockets of Tipu was taken by the British scientists and they re-engineered it. However, at that time, the German scientists had developed a very, very powerful rocket called the V1, V2. And the V2 rocket burned about 8,000 kgs of propellant, basically liquid oxygen and alcohol, with an oxidizer to fuel ratio of about 1.3 for 65 seconds. And the exhaust gas velocity, as I mentioned earlier, was 2,000 meters per second. So this was used extensively during the World War II, especially against the British. Now the question is, what does a rocket push against? Now all of you have seen cars push on the road, boats push on the water. Even when we run, our legs basically push against the ground to move us forward. And so you need something to push against. Jet against, push air through turbines, heat it, push it against hot gases out. What can you push against in space? As I said earlier, rockets can work in space where it is near vacuum conditions. So what can it push? So there was a lot of skepticism initially when Professor Goddard in the US started working on rockets. His work was ridiculed by most of the people in those days. So I have a quote here from the editorial published in New York Times in January 13, 1920. And it made a mockery of Professor Goddard's research work. I quote, that's in the red thing here. Professor Goddard does not know the relation of action and reaction and of the need to have something better than vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge rattled out daily in high schools. So, this was the understanding of the common people, saying that Dr. Goddard was some kind of a stupid guy who didn't know basic physics, but he was the father of the rocketry in US. So, very quickly, people realized rockets work in a slightly different way. So, in a nutshell, rockets push against the inertia of ejected gas. So imagine standing on a sled throwing bricks, and conservation of momentum says the brick takes away a certain amount of momentum, and the same momentum is carried back into the main sled. It's like, let's say you're sitting on a chair with wheels and you try to push the table. The table may not move, but the chair will move backwards. So that is the conservation of momentum. And as I said, if you throw a bricks, each brick carries away momentum, adding to your momentum. So it can, of course, can eventually get going faster than you can throw the bricks. So this is an important point. While you can throw the bricks at a certain velocity, the rocket actually can go faster than that because it's additive. We'll see that how that happens in a short while. So this is the one I said. This is a nice picture from a textbook which I borrowed. All copyrights, no claims to originality is made by me. This is a nice picture. This is educational purposes. I borrowed it. So it says a person sitting on a sled like this, and assume there are no friction losses with the tire on the ground. He throws a rocket. So what happens? Imagine the trolley has about 100 rocks of the same mass, each one of them, and he has two options. Of course, assume that there is no friction and drag. What happens if he throws a rock? What happens if he throws all the 100 rocks at the same time? No, he has option. He can pick up all the 100 rocks and throw them out at the same velocity, whatever he can, or he can throw one at a time. Which do you think will be better? So that's an interesting point, which we'll try and resolve shortly. Okay, so here is a small Excel example I have built. The initial velocity, assume the vehicle is zero. I mean, it stands still. Let's assume the vehicle mass is about 1100 kg, 1100 kgs, and the rock mass is about 100 kg. And let's assume that there are a number of rocks he has got are 10, and the velocity at which he can throw 10 meters per second. Of course, this is a little on the higher side. A 100 kg thing you cannot really throw, but just for calculations and round numbers, I have made it like that. So when you throw a single rock of mass 100 kgs at 10 meters per second, the momentum of each rock then would be 1000 kg meters per second. Okay, so this is the basic data. Now let's see. He throws all the 10 rocks at the same time. So momentum carried away would be again kg meters per second. 10 into 100 into 10. That's basically 10,000 kg meters per second. And since the vehicle mass from which he's throwing when he threw was 1100 kg, so this will add to the vehicle will get about 9 meters per second velocity in the direction he wants. So the net delta V the sled is getting is about 9 meters per second. Let's say this when he throws all the 10 at once. Now let's say he's smarter. He throws first 5 bricks at a time. First 5 bricks when he throws, the momentum carried away by the bricks is 5,000 kg meters per second. Again, the vehicle mass when he threw was 1100. Now velocity it gets is smaller because the momentum carried by the rocks is smaller. He gets 4.55 meters per second increase in velocity of the sled. After that, he throws the next 5 rocks. The same calculation, 5,000 momentum taken away. But now the vehicle mass from which he throws it is not 1100, but it is 600. Because it's 600 kg, the velocity increment is roughly about 8.33 meters per second. So net velocity he gets is nearly 13 meters per second. If he threw all the 10, he would have got 9. If he threw 5 and 5, he would have got 12.88. You can extend it to saying that if he throws one rock at a time, he'll get much more. But of course, after some time, it kind of asymptotically floats out. So as you can see, throwing 5 rocks at a time is better than throwing all the 10 at the same time. We will come back to the same point later because this can be directly connected with the propellant burn rate. For example, saying that he threw all the 10 rocks at the same time is like firing a gun or a cannon where there is an explosion and the bullet leaves the round leaves the barrel and that's it. No more propulsion is there. So at one time you give it the impulse. So the next one is like a two-stage rocket where you initially you give it a velocity increment and then you give it a velocity increment second time. So this we'll come back to this in a little later time. So let's look at what is needed to put something in orbit. We will discuss also the orbit shortly, but assume that you want to put something at a 200-kilometer orbit, which is about the lowest orbit altitude where a stable orbit can be maintained, approximately 7.7 kilometers per second. Assuming gravitational plus drag losses of 1.7 kilometers per second, we need about 9 kilometers per second velocity increase. So even accounting for a velocity addition due to Earth's rotation, that's about 430 meters per second. If you are launching in the same direction as which is Earth is rotating, the highest energy content propellant combination as of now, chemical propellant, liquid hydrogen and liquid oxygen, gives you a velocity of about 4,000 meters per second. And this would require the mass ratio, initial and final, about 10. So this represents a very high structural efficiency, which is right now, which means that if you want to be able to launch something, put something in orbit at 200 kilometers with a single stage rocket, it's not reasonable, and it's not with the current technology, you cannot do it. Okay, so which means, like as I said earlier, throwing all the 100 rocks at the same time, you will not be able to put anything in space. So instead, you can throw it in 2 steps, right? So that is the staging logic which is used in launch vehicles. You have a first stage, which takes the whole rocket up to a certain velocity. Then the first stage is discarded. The second stage fires on, and that gives it a velocity. So now you can have final velocity delta V1, delta V2, delta V3 to up to delta V1. This will be a large increase. Of course, more than 3 stages is not really beneficial because every time you have a separate stage, it comes with its own control systems, its own nozzles, its own fuel tanks and everything else. So the mechanical complexity, the weight of the stages increase. So the benefits after 3 or 4 stages taper out. It's no longer useful. Most of the launch vehicles are around 3 or at best 4. So I said putting something into orbits. So what does it mean going into orbit? So we know right now we are used to assuming the Earth's gravitational constant for acceleration is about 9.8 meters per second. But we also know that it reduces as we move away from the Earth. Okay, that's from the Newton's law. The further you go from the Earth, the acceleration to gravity reduces. Now let's imagine launching a succession of rockets upwards, or even basically you throw a cricket ball up. If you throw it at a low velocity, it will go certain height and come down, fall down to earth. You throw it at a higher velocity, it will reach higher altitudes, but eventually it'll come back and fall to the earth because of Earth's gravitational pull. But suppose you throw it at 11.2 kilometers per second, of course, which is absurd. Nobody can do that kind of thing. But imagine you have some mechanism of shooting the cricket ball into space at 11 kilometers per second. Then it will overcome the Earth's gravity and will not fall back to Earth. So, what do we mean will not fall back to Earth? Imagine, let's say you're on the flat ground and you're a nice cricket enthusiast and you throw a cricket ball. After some time, remember the cricket ball will hit the ground, right? You must have seen that. Even if you threw from the in a long on boundary, it'll eventually reach the some point on the ground, it will fall. So in this case, if you throw it at a horizontal speed faster and faster, the distance on the ground will increase. But one thing is important. Basic physics says that the ball will fall to the ground uh, in a second. It will fall about 5 meters per second. Now, if you remember the basic school dynamics thing, distance s is equal to initial velocity ut plus at square. In this case, the only force acting on the ball is the gravitational force in the downward direction. That is 9.81. Ut initially, if you throw it horizontally, u is 0. So in about time t, about 5 meters, it will fall. So okay, if you throw horizontally faster, it will go x distance further, but it will still fall down in 5 meters in a second. Now there's another interesting point. If you look at the curvature of the Earth, Earth is curvature, spherical in shape, its curvature, you see that at the right picture, at a distance of 8 kilometers, the Earth's surface has moved away from your eyesight by about 5 meters, which means that let's say you have a tower at this point, which is 5 meters tall. Then, if from your standing point, you will see only the top of the tower. Okay, so essentially, Earth's curvature is such that it dips about 5 meters after 8 kilometers. Okay, so what I want to say here, suppose the cricketer is able to throw the ball horizontally at about 8 kilometers per second, it will keep falling. That is fundamental physics. But you will never touch the ground because it falls 5 meters, but the earth has curved away. Okay, basically in that case, it goes into orbit. This is a very simplified, kind of an explanation. Of course, the question of resistance to air drag and all that, but we'll talk about later. So if I can throw anything at 8 kilometers per second and above horizontal, I mean in this case, circumferential around the Earth, it will go into orbit. Okay, so now let's look at typical orbits. I'm not going to talk detailed into orbital mechanics, just to give you a flavor. You want to put something close to Earth or low Earth orbit, you need a minimum of 7.6 kilometers per second velocity, circumferential velocity for it to do that. And let's say, and if you want, as I said earlier, you put first in the Leo, and then you want to put it to some other orbit. You want to make it circular orbit, or you want to take it to Moon or the Mars or whatever. So let's say from low Earth orbit, you want to take it to Mars. The time duration will be 0.7 years, and the velocity increment you need is about 5.7 over and above 7.6. Okay, just for interest, let's say you have managed to do something to go to Alpha Centauri, which the one of the nearest stars available to us. It'll take you 50 years, and the velocity increment needed about 30,000 kilometers per second. So this is just a matter of interest. I thought I'd put it there. And also, let's talk about types of orbit. So as I said, not to orbit, a spacecraft around the Earth, it must be launched at an elevation above the Earth's atmosphere so that the drag doesn't slow it down. You want to take it away, let's say at least 150 kilometers above the Earth's surface, where the atmospheric condition is almost vacuum conditions. And there'll of course be still residual gases and all that. So anything above that, you can achieve that orbit. The more energy efficient orbit is achieved when the spacecraft is launched in an eastward direction and as near the equator as possible. As you know, the Earth is rotating over its axis, and the velocity of rotation will be the largest at the equator. At the pole, you may not see much of a difference. So, since the Earth is rotating in that direction, it is better to take advantage of that and launch your spacecraft or whatever in the same direction as the Earth's rotation. So that will give you quite a bit of a free ride. And for example, in Cape Canaveral, where the Apollo and the space shuttles are all launched, it's about 28.5 degrees north and due east. So you get a free ride of 1.47 kilometers per hour additional velocity. Okay, and India launches its vehicle also on the east coast and Sriharikota, and so that is again you get little more advantage because we are only about 14 degrees north as compared to Cape Canaveral, so we are closer to the equator. So you take advantage of that Earth's velocity. Okay, so if we put space shuttle is a very popular thing which most of us have seen, fascinated, which looks like an aircraft. Is also launched into space, and it was launched into about low Earth orbit, about 200 kilometers altitude above the surface of the Earth. It had a period of 90 minutes, meaning every 90 minutes it would go around the Earth, and its velocity was about 7.8 meters per second. Of course, even at this altitude, there are certain residual gases which eventually slow down the thing. Once the V goes down below this, then it starts falling to the earth. So basically, it's not a long-term parking option for any satellite. Space shuttle is okay. It was supposed to work only for 4 or 5 days and come back to Earth. But you want to put a satellite which you want to stay there for years together, then you have to take it much higher altitude because of this uh, losses what you see. The other popular orbit is what's called a geosynchronous orbit. These are circular orbits on more or less above the equator, and their period is 24 hours, meaning they go around the Earth once 24 hours. And incidentally, Earth also goes around at this around the same period. So from the Earth's point, it looks like the satellite is exactly placed over the same point from where it was launched, because both are rotating at about the same period. So, and such spacecraft are called geostationary orbit, and this orbit approximately is around 36,000 kilometers above the equator. Most of the communication satellite like GSAT, INSAT, or any other satellite through which we get our television channels and other communication things, they're all geostationary satellites. So this is there's another type of orbit which is also used. This is called sun synchronous. Basically, you take a video of a spot on Earth exactly at the same time every day. Okay, so if it is passing over Bangalore at 2 o'clock in the afternoon, it will keep passing over Bangalore exactly at 2 o'clock afternoon, day after day after day. So the advantage of this is it can take video pictures at the same angle and the solar illumination on the surface. So this is very useful if you are looking at forest spread or agricultural growth or even border areas. So let's say typically you're trying to have a look at what's happening in the northeast or northwest border, and of course this is a very good thing. So you can take pictures of the same. Let's say you're interested in the build-up, enemy build-up in Galwan or in the Saishan. Every day you take pictures at the same time. Any change you can easily quickly do. But the disadvantage is that propulsive maneuvers to adjust a bit or a lot of you know expensive maneuvers. So this is not again a long-term thing, but a lot of things are launched. This unsynchronous orbit. Initially I talked about transfer orbit, right? Put something first in the transfer orbit. From there you move it to whatever orbit you want. So let's take the example of what's called apogee boost. Apogee stands for the point farthest from the Earth, and perigee is the point very close to the Earth. So this is a ISRO press release. They said the satellite was placed in a geostationary transfer orbit. It's not geostationary orbit; it's a GTO, transfer orbit, with a perigee about 180 kilometers. The nearest point to Earth was 180 kilometers, and an apogee of 36,000 kilometers. So that is the target altitude in which you want the satellite to be placed. So rocket sending a payload station is drop off the payload. Then halfway point, these are actually halfway points in order to the satellite's final position. Final transmit orbit, a satellite conducts engine burns to circularize the orbit. Okay, so when it is at the apogee, the farthest point, they fire a rocket which will increase its velocity. So what it does is at the 36,000 kilometers remains same. 180 becomes, let's say, 250, 250 becomes 1000, 1000 becomes 5000. So eventually it'll also become a 36,000 kilometers. So both perigee and apogee will be around. That means it's a circular orbit. So whenever you want to circularize an elliptical orbit, the usual maneuver is apogee boost. And this is what was used for GSAT. Let's take the next maneuver, which is ISR orbit. This is for Chandrayaan. Again, it said, the press release said, was launched into initial Earth orbit with a perigee of 170 kilometers and an apogee of 40,400. I want you to note this. It's not 36,000 as GSAT. This is 40,400. And here too, in this case, what they did, instead of apogee, they started firing the motor at perigee. When it's closest to the Earth's surface, the velocity will be the highest. That's the normal thing. So at a very high velocity, even if a small push you give, the apogee, the other part will move away. So essentially, this trying to firing rockets at the perigee is to increase the ellipticity, and eventually it'll take you out of to the Earth's orbit and into the moon. In this case, of course, moon, and the Mars also it was something similar done. So let's look at what happens here. So the star is supposed to be the Earth. That's where the Earth is there, and this is the point closest to Earth, perigee, and the satellite is in elliptical orbit like this. This is the apogee point. So when it's at perigee, the velocity will be very, very large. In this case, what you do is even a small impulse here will make this ellipse bigger and bigger. So this point, apogee point, will move further and further away. And then, of course, it'll escape the Earth's gravity and then be trapped into Moon or Mars's gravity and go in that direction. Okay. Other than that, you can look at apogee. In this case, the same Earth is at one of the foci of the elliptical orbit. When it is at the furthest point, you give it an impulse. So what it does is it will make it more and more circular. Eventually, you will be putting it into geostationary orbit. So whenever you want to put something in geostationary orbit, you make it, you give apogee boost. And whenever you want to take it out of the orbit into some other interplanetary stuff, then it's a perigee boost. Just I'm not going to great detail. These are, of course, not as simple as I have explained here. These are very, very complex maneuvers, but the idea is to give you a flavor of what is being done here. Why? So far we looked at the basics of launch vehicles and orbits and all that. Now let's look at trajectory. How do we fire it, or why do we fire it in the way we want? Now there are two options here. You can fire the rocket straight up vertically, or you can fire the rocket at an angle to the horizontal axis. So we'll see why and how things are done like that. But if you've seen the videos of launch vehicles, they seem to be going vertically upwards, which is also true. So if you look at, again, simplifying and skipping a lot of technical detail, because that will be part of your actual course. This is more like a YouTube video where you watch whenever you have time. So I will not go into too much of detail. So assume this is the rocket. It's tilted at around theta degrees. Theta, if it is 90, of course, it will be vertical like this. Some theta degrees is there. It's pointing in this direction. And you fire the rockets. So the force you thrust, which will be in this direction, mark T here, and the exactly opposing the thrust will be drag, right? Now, assuming that there is no lift produced, and most of the launch vehicles have very, very small lifting services used mostly for controlling. So lift part you can ignore. It's mostly drag and thrust and gravitational force. So Newton's law says mass into acceleration, that is m into dv by dt, is equal to the forces on the right side. So what are the forces? One is the thrust produced by the rocket. Second is the drag. And since drag and thrust are in the same direction, it is just T minus F or suffix D. But there is a gravitation force acting, mg. Okay. So now that is acting in the direction. So you have to add that into. So mg into sine theta is also one of the forces acting. Okay, so this is the m dv by dt equal to T minus F of suffix D minus mg into theta is the Newton's equation. Now you can, of course, divide m, of course, to simplify equation, you divide m on the right side. M is basically not a constant, of course, because you are burning propellants, but we'll handle that later. In this case, we just simply take m on the right side. It will be T by m into dt for integrating fd by m into dt minus g sine theta dt. So if I integrate this equation, dv by dv is equal to minus I sine thing, integrating, I'll get this equation. ISP into G naught into dm by m. Again, I'm skipping many steps. You will see in your class notes later. G now, I'm assuming also that the G, I'll take it as a gravitational constant on Earth, which is simply G naught, basically 9.81. Of course, this will keep reducing as you move away from the Earth's surface. But to simplify the matters for easy understanding, I will take this as a constant so that then it will be easier for you to integrate. Similarly, drag is simply represented as f of d by m into dt. So if I want to see the velocity increment I am able to get, I just have to integrate this from dv from 0, v is equal to 0 to v is equal to whatever time. And I am what I have done here in the previous step, I think it's better I clarify here. Let's go back to this. Thrust. Thrust produced by rocket depends on two things. One, the mass flow rate, m dot, and the specific impulse of the propellant and the g naught. Now, specific impulse unit is second. You multiply it by g naught, that is meters per second squared, and then you multiply by m dot. M dot is kg per second. So you will get thrust. So T is replaced by this, and G naught and FD. So if you assuming G naught constant, meaning gravitational constant doesn't vary with altitude, then you can take it out of the integral. ISB is anyway a constant given for a propellant combination. Now, like if it is log ox hydrogen, it is a 1 ISP, and if it's some other solid propellant, ISP is constant. So you have this constant outside, dm by m minus g sine theta, g naught into integral 0 to t naught to t sine theta theta minus integral t naught to t f of d by m dt. Now here the problem starts. G naught into sine theta, G naught you can assume is a constant from the surface of the earth, so it's easy to do that. Sine theta we can integrate from t dt, t naught to t. But drag, of course, depends on the velocity square, which is part of the velocity you are trying to get. So this becomes a nonlinear part. Now, if you want to integrate to a time t, what time? So I would say that when my propellant is completely burnt, I'll call that TB, it's called the burnout time. I want to integrate from time 0 to burnout time. So if I'm going to burn out the propellant for return, I want to see what's the velocity maximum I've got. So that means this integral will be VB minus V naught is equal to, I have interchanged the limits here, it becomes G naught ISP into ln m naught by mb. Okay, m naught is the original mass, mb is burnt out mass. Okay, the rest I'm going to keep it here. So this part I have indicated, G naught integral 0 to TV sine theta. It's called gravitational loss or the reduction in velocity due to gravity. After all, you are working against the gravitation um, by for this. One way to understand this or picture this in your mind, imagine yourself you're running on a flat ground, and imagine next you shift to a ground which is sloping up the hill. Can you run at the same speed up the hill with the speed at which you're running on the flat ground? If you want to do that, you need more effort because you are working now against gravity. Okay. Similarly, if you're running downhill, you need less power. Run downhill at the same velocity because now gravity will be assisting you. So this is the velocity reduction you need to take care of by gravity, meaning you have to overcome this. Similarly, there is a reduction in velocity due to drag. And that is depends on the CD drag coefficient of the rocket, and it depends on the area cross section area and v square and a whole lot of things, and also m is into that. So the as a first step, let's say we neglect the gravitation losses and the drag losses. So if we do that, this entire term disappears. So you have only delta v is g naught ISP into logarithm of ratio between initial and final mass. It's a very simple equation. Okay, and we will try and see how we can estimate these things later. So if I ignore the losses due to gravity and drag, equation simplifies to G naught ISP into ln r. Ln r is the mass ratio, where r is initial mass by final mass. Okay, now what is the final mass? Initial mass is the structure, the metal, the nozzles and the electronics and the payload and everything else plus propellant. The final mass will be simply m naught minus the propellant mass. Propellant is one which is burnt out. So mb is whatever is remaining after the propellant is burned out. Okay. Specific impulse, if I want to get a higher and higher velocity improvement, then I can increase the specific impulse. But there is a limit to chemical propellants having the specific impulse. Not much I can do about it. But I can also increase this ln m naught by mb. Okay. But right now, r is less than 10, and that about thing, which means that if I have a initial launch vehicle is 100 kg mass, 90 kgs is the propellant. That would be very difficult to achieve, and that's about the limit. You cannot go beyond that. So which means that the velocity increments with a single stage, it is not much you can get uh, with the present technology. So the concept of maximum attainable delta V in a gravity-free environment may seem, rather naive or inapplicable, because there is anyway gravity is there, there's atmosphere is there. What about the drag and what about the gravity and all that? Actually, the variations still play a role in flight environments where gravity and aerodynamic forces have to be taken into account. But having said that, if we can still use this simple delta V relation with G naught ISP into ln of m naught by mb when you're comparing two propulsion systems, because the rocket sizes are going to be similar, so which means that the CD and the cross section area, all that will be similar. So when we compare the two different kinds of propulsion systems, we can use this delta V to find that. Uh, and of course, when you want to upgrade from one system to another, you can use this as a measure. All the while remembering that this is the approximation, but useful in practice. Now, initially, while we ignored the losses due to gravitational drag, we need to find ways to estimate it or try and reduce them. But the issue becomes a little complex here because the ways to reduce the loss they oppose each other. So when we say minimum loss due to gravitation occurs when the time interval is zero. Remember, gravitation loss is integral g naught into delta sine theta into delta t. So the smaller the delta t, the lesser the gravitational losses. Which means that the time interval should be zero. It's like cannonball or a gun bullet. Highest initial velocity at the instantaneous time. So this will have a very low gravitational loss. Okay, but when you have the highest velocity at the surface of the Earth, where the air density is also high, the drag will be enormous. So if you want to minimize the drag due to loss due to drag, when the vehicle accelerates slowly through the dense atmosphere, it becomes faster and faster as it goes higher and higher altitude. So let's say it crosses 50, 60 kilometers altitude, and then it becomes faster and faster. So the drag loss, if you want to reduce the drag loss, I have to accelerate slowly in the atmospheric condition. If I want to reduce the gravitation loss, then I have to fire instantly. So in this acceleration basically is a factor of what's called a thrust to weight ratio or the thrust loading. Because finally, why should the rocket move? Unless the force which is being exerted on it is more than the gravitation force and the drag force, it won't go, it won't start rising. Basically, the thrust to weight ratio of the propulsion system should be more than one for it to rise. For example, a helicopter's thrust to weight ratio is close to 1.3, 1.4. That's why they're able to go right up, straight up like that. And a rocket too has to be that. Now I have options here. I can have a very high thrust to weight ratio, let's say 4 or 5 or 6, whatever. Or I can have 1.1, 1.3 like that. So, and most of the propulsion of the multi-stage vehicles presently in use is around 1.5, implying initial vertical acceleration about half. One it means t is equal to w, so 1.5 means you need half g naught acceleration possible. We'll see why this is so, why this is advantageous, and why people tend to use this. Just to show you the effect of mass ratio, which I talked about earlier, this is a nice worked example from again from a textbook, which I have borrowed for education purposes. Consider a vehicle for a vehicle in gravitation-less space. Determine the mass ratio to boost the vehicle velocity 1600 meters per second. Basically, from zero, you are giving it a velocity, final velocity of 1600 meters per second. And B, the same vehicle, I want to make it 3400 meters per second. If the effective motor exhaust velocity is 2000 meters per second, meaning the gas velocity, motor velocity is 2000 meters per second. If the initial total mass is 4000 kgs, so the rocket is 4000 kg mass initially, and the propellant velocity, exhaust velocity is fixed 2000 meters per second. That is G naught into ISP is fixed. And I want to put it, I want to give it a boost of 1600 meters per second. And in option B, I want to give it a boost of 3400 meters per second. So what should be the propellant ratio? Now let's look at the option A here. Delta U is 1600 meters per second, and boost vehicle, so initial zero is there. And delta U, as we see, the simplest equation is C, that's the exhaust velocity, into ln1 mr, the mass ratio. From that, you can work out that the mass ratio turns out to be about 0.4493. That's 16,600 by 2000. This is the main thing, 1600 to 2000 e to the power minus that. If you take, you will get that. From that, you can final mr is final mass by initial mass. From that, you can work out and find out the propellant mass is around 2300, 2200 kgs, roughly more than half of the mass of the entire entire rocket is propellant. And this is if you want to give it 1600 meters per second. Now, the same condition, same propellant, the same initial mass. What if I have to do it to take it to 3400 meters? Then the propellant will be mass itself be 3269 kg. So out of the 4000 kgs, 3269 will be propellant. But then you may ask the question, what about the structure holding the propellant? What about the nozzle weight? What about the electronics? And what about the propellant? So see, this is why it becomes more and more difficult. And there is structural engineering limitations on how much you can take in a rocket. So that's why most of the things go into multiple stages. So commenting on the example, as I mentioned here, it takes about 2,200 kg propellant to get the vehicle up to 1600. It takes nearly 3,000 to get the vehicle up to 3,400 meters per second, which constitutes a mass ratio of, meaning 92% fuel. And of course, the chosen motor will dictate what type of payload mass you can launch, because whatever you have left now maybe is only 10, 15 kg, because the rest of it will be the equipment, and you're spending enormous amount of propellant to giving it a velocity of 3,400 meters per second, but nothing much you can put there. And the end velocity will heavily dependent on the amount of fuel we can launch with the vehicle. So there is a limitation to that. And this is the reason, one of the reasons, if I want to, let's say, put something in space, give it at least 8 kilometers per second, it's practically not possible right now with the around technology available. Okay, now there's the simplest launch, as I said. No, you instead of launching it at an angle theta, suppose you launch it upwards directly. Like I said, you pick a stone and throw it right up in the sky. Simplest case. This was proposed by Dr. Goddard, and he says what should be the maximum altitude you can get. Okay, so the rocket is launched at vertical, that is theta is equal to 0 in that equation, where the rocket goes straight up. The question is, what's the maximum height it can reach for a given propellant type ISP and weight? Okay, so does the initial thrust to weight ratio have any effect on it? If so, what should be the thrust to weight ratio to maximize the heat. Now, in this, sorry, not heat, height. Thrust, as I said, that depends on the propellant burn rate, m dot, into g into ISP. G into ISP is the characteristic velocity, and burn rate is kg per second. Together, they end up in the force unit thrust. So, rapid propellant burn rate means if I increase this for a given ISP, specific impulse of the propellant, if I increase the burn rate, then the thrust to weight ratio will be very high. The thrust will be very high. Now, I want you to spend a little more time here trying to explain this. So I can either have the same propellant burning very high rate in terms of kgs per second, or I can have it at a slower rate. If I do it at a slower rate, the thrust will be lower, which also means the thrust to weight ratio will be lower. So now let's look at what happens if the high thrust to weight ratio is there. Let's say the thrust is 4 times the weight. It means that the acceleration is be very rapid, very rapid acceleration, which also means drag losses, but lower gravity loss, right? Larger drag loss because it will be high velocity at high density atmospheric conditions, which means large drag, and about it'll be for lower thrust to weight ratio, it'll accelerate slowly, drag will be less, drag loss will be less. So this is the thing. So now let's work out the problem instead of going theoretically. And of course, people have solved this theoretically using variational calculus and all that. For the explanation purposes, for this kind of cash, you can say semi-formal talk, I'd rather use a calculation procedure. So this is again a problem I picked up from the book. I believe it's from Professor Ashish Tiwari's book. He talks about initial mass of the vehicle is 20,000 kg. It is launched vertically, just velocity of 1 meters per second. To avoid some numerical error, I just put 1 meters per second. Final payload mass should be, final payload mass should be 2,000 kgs. That's what you want to put into orbit. Assume the rocket to be a single stage, okay, with a specific impulse of 300 seconds and a constant drag coefficient of CD naught based upon reference area of S is equal to 2 meters square. So I have CD, I have area, then if I have the velocity, I'll have the drag loss. So the Earth's atmosphere is assumed to have an exponential model, uh, and a model where rho naught is 1.752 kg per meter cube, and H naught is 6,700. This is a model which is what is actually density varies. Lowest values of the surface 1.225. It varies very rapidly. So people have worked out an exponential model using this kind of it is a fit, basically an exponential curve fit of the way density varies from here to about 70-80 kilometers altitude. Simulate the external trajectory of the rocket for thrust to weight values from 1.0 to 4.2. I'm just assuming if it is 1, of course it doesn't make sense, so I'll start at 1.2 and go up to 4.2 and plot the maximum height and velocity at burnout. Of course, this problem was originally proposed by Dr. Goddard, whose picture you can see on the right. Okay, now we talked about gravity and drag losses. So let's see how it works out. Gravity losses delta Vg and the drag losses are the most significant loss terms. They are primarily dependent upon the initial thrust to weight. Here is where the pinch comes in. T by W or thrust to weight ratio has an impact on the losses with gravity and all. So if you see the blue curve, this is the delta V or the reduced velocity because of gravitational losses. And that from 900 meters per second at a low thrust weight ratio, because low T by W means you're spending more time in the working against the gravity, it goes down further to 4. When the T by W is 4, the gravitational loss is the lowest. Exactly the other way, the green line indicates the drag losses, which is very low at low T by W, increases no, rapidly when the T by W is 4. Okay, so T by W, of course, needs to be greater than unity for the vehicle to leave the launch pad. And you'll find the typical lift-off thrust-to-weight ratio in the present scenario is about 1.32 in all the existing portfolio of launch vehicles. So why is it like that? So when you actually, I've written a small Python code, which I will add in the list. We can download and check it out. And by the way, that Python code is written more for understanding. I'm not a Python programmer, but I've tried to make it because it's open domain and you don't need any compiler other than whatever is there in Unix to be able to run that. So if you program that, if you run that program, and I've run it from different one point, test to weight ratios, you find that the velocity at burnout, okay, when the test to weight ratio is 4.5, the velocity at burnout is around 5.5. 5.5 or something meters per second, very high velocity at the burnout. Okay, but at lower thrust to weight ratio, the burnout velocity is lower, and this is of course because of the losses. Okay, for last T by W, propellant burn rates are high, and the vehicle accelerates rapidly. Higher delta VD loss due to drag, lower gravitational V. So because of lower gravitational losses, you're able to achieve a higher velocity, right? So now this is something interesting. So now if you look at the height at burnout, what's the maximum altitude? This is the other way around. You get the maximum altitude reached when your thrust to weight ratio is less than 1.5, is around 1.3, 1.35. At higher and higher thrust to weight ratio, your altitude reach is reduced. So for lower values of T by W, propellant burn rates are slower and the vehicle accelerates slowly through the atmosphere. Lower loss due to drag, higher loss due to gravitational losses due to gravity. Okay, then why is it that you get a higher altitude when you are able to burn thoroughly? This goes back to my initial example of throwing rocks. Lower propellant burn rate means like you're accelerating slowly, and it's like throwing two stones at a time instead of all the 10. So if you want to maximize the altitude of the reach, which is what you want to do if you want to put payload into orbit in a civilian kind of scenario, and then you have a thrust to weight ratio close to 1.5. However, if you want to do something else, let's talk about. So gravitational and drag losses are sensitive to initial thrust to weight ratio. A low T by W causes gravity loss to be high because the vehicle spends more time in ascent. For medium to large launch vehicles on normal trajectories, the vehicle loss due to gravity falls between 750 to 1500 meters per second. As we saw in our case, it was highest was 900 meters per second. While T by W causes drag loss to be high because of the higher velocities achieved at the atmosphere. For the current inventory of launch vehicles, and this is a key point you should note, the velocity losses due to drag are very, very low, or less than 3% of the delta V, and is about 20 to 40 meters per second. That's it. So even though I spent a lot of time talking about drug glasses, but they're not the thing, the important thing. The biggest thing is the gravitational part. So T by W ratio is a key launch vehicle parameter because it dictates the vibration, acoustics, dynamic load environment for a whole lot of things. I cannot have a T by W of 4 with somebody sitting inside, human beings or other things. So T by W is also, thrust to weight ratio is also limited by what amount of vibration, acoustics, dynamic loads your equipment can take. Okay, so even if there is no astronaut in it, they have other electronic equipment which may be affected by the vibration, acoustics, dynamic, and all that. By the way, this is from the reference Space Mission Analysis and Design, third edition, edited by William Wiley Larson and James Ward. So this is a very nice book which talks about entire analysis of space and designing how it's done. So key takeaways which I would like to talk about here is one, thrust depends on propellant mass flow rate and ISP or the propellant combination. So that is of course m dot into g into ISP. That's one thing. Terminal velocity reached by the rocket depends only on the mass ratio, initial mass ratio. That is m initial by m final ratio. Okay, and this cannot be improved beyond a point because you need to provide for a structure, you need to provide for control systems, electronics, nozzle, and all that. Unless you are able to find a technology where you burn that also along with the propellant, then it's like you must have seen that cone ice cream or softy ice cream where you eat the ice cream and the container along with that. Until that happens, this there is a limitation, engineering limitation on this ratio. So large terminal velocities can be obtained by high ISP and high initial and final ratio. Of course, both have limitations. There's not much you can do beyond a certain point. But the same propellant combination mass ratios, we can have different burn times. That is possible. Then longer burn time means lower mass flow rate and thrust. The height reached by the rocket or propellant burnout is more complex, depends on drag and gravitational effects and a whole lot of other things. Even in this toy example, we can see that the highest altitude reached by the rocket was actually with lower thrust to weight ratio, longer burn time. Finding the optimum combination of mass ratios, ISP, and burn time to maximize altitude for rocket is a complex variational problem. Maybe we have no time, and that needs full classroom scenario for me to explain those things. Some closing comments. We have seen that thrust to weight ratio impacts velocity and maximum height at propellant burnout differently. So how does one choose the required T by W? Well, that depends on the mission for which the launch vehicle is required. Let's say you're designing missiles, basically surface to air or air to air or air to ship or ship to air, whatever. Then the reaching the target, the enemy missile or enemy aircraft or enemy ship, as quickly as possible, the shortest time is of utmost importance. That is what you are interested in. You want to reach the enemy and shoot it down or sink it in the shortest possible time. This means rapid acceleration requiring T by W of 3 to 4. So that's when you choose. For missiles, you choose a thrust to weight ratio of 3 to 4. For longer range strategic or ballistic missiles, let's say the range is 8,000 kilometers, like Agni 5 and all that. Then, of course, they have to one. They can't travel all the time in the atmospheric thing because they will be having a lot of loss. So these kind of missiles normally tend to go outside the atmosphere, and then from the gravitation attraction alone, they follow the ballistic trajectory. So that's the idea. So you want to throw it at a higher altitude, then let it go into that. So in this case, altitude is important. So in such missiles, thrust to weight ratios are usually between 1.2 to 2. So for most launch vehicles with humans on board, T by W is usually around 1.3, and that's the norm which is most probably formed here. So I think I'll come to close of my talk. While I upload this, I'll also upload the Python program which I've written. It's written only for clarity. There's no attempt to make it efficient or elegant, nothing of that kind. It is simple, bare bones program which will run the T by W, and it will also print out the plot the velocities and other things kind of thing. So thank you for listening. Please share your comments if you have anything on whatever. If there are any mistakes I made, please feel free to point it out. Now that I'm retired, I have no access to your grades or marks, so you can freely comment or critique my work. I would try and improve it as much as possible. So thank you for listening. Bye.